All right, I hope everybody had a good day. And tonight we're going to be discussing internal resistance associated with series circuits. You can't really talk about internal resistance of a circuit without talking about a series circuit. Now, clearly we've already had some extensive study of series circuits, and I want to emphasize, especially for the online students, that the lecture notes that are posted on the website for week 5 are entitled Series Circuits. So actually the lecture notes are a little bit behind what we're actually doing in the lecture. Okay, so anytime that I'm talking about something that jumps ahead or maybe jumps back a little bit, obviously you can just click on the link for the next week or the previous week and have the lecture notes that correspond to that. Okay, internal resistance, a very, very important concept. Not a real difficult one, but some students tend to find internal resistance a concept that just isn't natural, even though you're going to find that the analysis makes it simple. Okay. Now, the reason that we need to discuss internal resistance has to do with the limitations of the circuits that we've studied so far. What I'm drawing right now is just a simple voltage divider, resistor 1 and resistor 2, and the source voltage. We'll just say that the source voltage is 12 volts DC. We've done quite a bit of analysis already on circuits like this. We know that this is a voltage divider circuit. We know that the current is going to be the same through every component in this circuit, and that's really the definition of a series circuit. A series circuit is a circuit in which the current is the same through every component. And if you can't say that, then it's not a series circuit. Okay, that's the acid test for a series circuit. The thing that's been a little bit unrealistic about what we've studied to date, which we're going to clear up today, is the capability of our power supply here, or our battery, or our regulated DC supply, whatever we're using. Okay, the way that it's drawn right now, there's nothing indicated in the drawing that would lead you to believe that this has any limitations at all in terms of how much load it could drive. In other words, we know it's got 12 volts. Okay, and we know that the current, or the electron flow anyway, is going to come out of the negative terminal of the battery. But there's nothing in the drawing itself or the schematic that that would make it clear to us that there's a limitation of this circuit. In other words, we couldn't power up the state of California with this battery, right? And everybody knows that just from common sense. But internal resistance is really what tells us what the limitation is of the device that we're using. Okay, and it also tells us a lot about voltage regulation and how much the voltage is going to change on the output terminals of a battery as the load increases or as you add additional hair dryers. Okay, so let me just first label this as what it is. We've been dealing with sources of power that are ideal. So all the way to date, all the circuits that we've been dealing with where we've had a battery, that battery is considered to be an ideal source, which means that theoretically we could power up the state of California with this battery. Okay? Now, the reason that we teach it that way initially is because we're interested in the students getting all of the techniques and all of the laws of physics and laws of conservation of energy somewhat mastered. Kirchhoff's voltage law, Kirchhoff's current law, Ohm's law, the idea of industry standards. Okay? And then what we do is we come back and we take a look at this circuit and we realize that, hey, wait a minute, there's nothing that limits how much current could be flowing out of this battery the way that it's drawn. In other words, it could be putting out a 0.5 amp or it could be putting out a 500,000 amps. And there's nothing that tells us that that's not possible. And that's where the concept of internal resistance comes in. So what I'm going to do is I'm going to redraw this circuit, but I'm going to redraw this circuit the way that it's drawn in application. If we were actually going to model the circuit so that we could see what the limitations on the source were in terms of how much current it could put output. What I'm going to do is I'm going to draw a terminal here and here. And these are going to be like the only points that we could actually touch or reference if we were going to measure the voltage or measure the current, okay, that was coming out of a source of power. So, for instance, if we went to Walmart and we bought a DC car battery, that DC car battery would have two terminals on it. One terminal would be positive, the other terminal would be negative. And that would be the only place that we would have access to that source of power. I mean, we could cut it in half with a Sawzall, but then all the acid would leak out and, you know, it wouldn't be a functional battery. Okay, so we can't actually get inside the battery. Okay, now there are some devices that we can get inside of, but what I'm talking about are devices that we're using in the field, okay, that we're using for a practical application. So what I'm going to do is I'm going to draw my battery much larger than I normally draw it. And I'm going to do that to emphasize this concept of internal resistance, keeping in mind the fact that the only place that we have access to measure the voltage on this battery or this source of power are at these 2 points right here. That's the only place. We can't get inside of it. Just like we couldn't get inside this battery right here to take measurements unless we did something that would, you know, puncture and subsequently destroy the battery. Now, what we do, and again, what we're focusing on here is internal resistance. The way that we model this is we take a battery that's an ideal battery. So this is an ideal battery, and that's like the ones that we've been working with so far. They've been ideal batteries. And we connect one terminal of that negative of that ideal battery to the terminal that's available to the outside world, just like on the battery from Walmart. Okay, that would be one of the terminals on the battery that's available to get energy. Then in series with the ideal battery is a resistor, and that's our internal resistor. So I'll just label it R sub I for resistance internal. Okay, and what we're going to do is we're going to give it a typical value. We're going to say that the internal resistance of our battery is 2 ohms. Okay, and then what we're going to do is we're going to see how the loading effect, or hooking up successive hair dryers, space heaters, blow dryers, whatever, has an effect on the voltage that we read at the output terminals of our actual battery. So what we're going to do is we're going to hook this up to just one single load. And we're going to say that the resistance of this load is equal to 100 ohms. So the resistance of the load is equal to 100 ohms. Okay? And then what we're going to do is we're going to draw an equivalent circuit. Okay? Now, would it be fair to say that this right here is a closed loop? Yeah, that would be a correct, fair statement. Okay, that's a closed loop. So if this is a closed loop right here, then although we don't know what the magnitude of the current is yet because we haven't calculated it, what do we know about the current?
What do we know about it?
The current. The current that's flowing through this circuit.
Direction.
Right, it's going to leave the negative terminal of the battery, and it's going to flow in a counterclockwise direction, and it's going to be the same in every component because it's a series circuit. In other words, the current coming out of the battery is going to be the same as the current going through the load resistor, which is going to be the same as the current going through the internal resistor. Okay? So what we're going to do is we are going to simplify this circuit by drawing it the way that we're used to seeing it, where we have an ideal source, and then we have a resistor in series with another resistor. This resistor is going to be our internal resistor. Now, does it matter that we moved our internal resistor outside of the box? I mean, for the purpose of doing the analysis? It makes no difference whatsoever. Okay? So we moved the internal resistor outside of the box for the purpose of doing the analysis, and that had a value of 2 ohms. And then we bring down the resistance of our load, and that had a value of 100 ohms. And then what we're going to do is we're going to say that our source voltage, when it's unloaded, our unloaded source voltage is equal to 12 volts. So we'll kind of compare it to what we'd find in a car or an automotive application. Okay, now, because these two guys are in series with each other, right, what would the formula be for combining those two resistors into one resistor? We just find the algebraic sum of the two resistors, right? So if we want to find our total, that's going to be equal to our internal plus our load, which is going to be equal to 102 ohms. Is everybody with me? So we just combine those two resistors, we got 102 ohms. Okay? So now, using Ohm's law, we could even further simplify this circuit where we showed the ideal source. So this is 12 volts connected up to one single resistor, and we'll call this resistor internal, comma, load, and that's equal to 102 ohms. Okay? And then use our simple Ohm's law formula. Resistance is equal to, I'm sorry, I didn't want resistance, I wanted current. Current is equal to, and you tell me what the formula would be for current if we know the voltage and we know the total resistance. E over R. So current is equal to the ratio of voltage over R total. And our total resistance is the sum of the internal resistance and the load resistance. Okay? Any questions? Pretty straightforward? All right. So we're going to plug the numbers in, and we're going to find out, if you get your calculator out, that we have 12 volts divided by 102 ohms. What's the current? 0.118 amps. That's the current that's flowing. So as we move back to the circuit that we started out with, we can then write down what the current is that's flowing in this circuit. We find that the current is equal to 0.118 amps. Okay? Now, if we were to change our load value, in other words, let's say that this represented 4 hair dryers plugged into a surge suppression strip. Okay? And we're going to increase the load by plugging 40 hair dryers into the surge suppression strip. Is the value of this resistance and the load going to go up or going to go down? It's going to go down, right? Because the resistance has to go down when the load goes up because they're inversely proportional with each other. Okay, but the first thing that I want to do, before we actually do that, is I want to calculate what the voltage drop is across the internal resistor. Okay, so the voltage drop across the resistor internal is going to be equal to IR, the current that's flowing in the circuit multiplied by the internal resistor, which is equal to 0.118 amps times 2 ohms. What does that equal? How much? 2.36.
I'm sorry, 0.236.
0.236. And that's going to be volts, all right?
Right.
0.236 volts. So what that means is that if we were to somehow have the ability to get inside of our load, of our source, I'm sorry. If we had the ability to get inside of our source, then when we took a measurement of the voltage drop across the internal resistor, that voltage drop would be 0.236 volts, right? So what does that mean? And this is the key to understanding the effect of internal resistance. What does that mean about the voltage that's available at these points right here?
It's lower.
It's decreased, right? Because if we started this guy out at 12 volts, our ideal battery at 12 volts, our ideal battery has been now reduced at these terminals by an amount equal to the voltage drop across the internal resistor. Okay? Is everybody with me on that? All right. So, in this particular example, if we were to take a voltmeter and connect it between these 2 points right here, what would we get? What's 12 minus 0.236? 11.7 volts. So that's the actual usable voltage that we would get out of the actual source of power, because there's current flowing and there's a voltage drop across the internal resistor. Okay? Now, to further emphasize this, we're going to change the load amount by adding 40 hair dryers, or the equivalent of that. Okay? And we're going to look and see how that changes our available voltage at the output terminals, okay, of our source of power. So what we're going to do is we're going to, since we know that as we add more and more hair dryers, the total load resistance gets lower and lower and lower and lower, right? So at some point, if we added enough hair dryers, we could get a load resistance of approximately 5 ohms, right? Might take 100 hair dryers, I don't know, but at some point we could get to a total load resistance of 5 ohms by adding enough hair dryers, okay? So now let's go back and let's reanalyze our circuit when our load resistance has changed from 100 ohms to 5 ohms. The number's gone down, which means the amount of load has gone up, or the number of hair dryers connected has gone up. Okay? So all we have to do is follow back through the same analysis that we did before. We have our ideal source, which is at 12 volts. We have our internal resistance, which is at 2 ohms. That doesn't change. That's the same as it is here. Our load resistance has changed from 100 ohms to 5 ohms. Okay? And our total load, or our total resistance, has changed from 102 now to what? 5 and 2. The internal resistance is 2 ohms, and the load resistance is 5 ohms. And when we sum those up algebraically, we get 7 ohms. Okay, so our total load resistance for the entire circuit is 7 ohms, including the internal resistance of the battery. Now, if we come over here and we recalculate what the current is that's flowing in this condition, our total resistance, including the internal resistor and the load resistances, we found was 7 ohms. Okay? And so now, the current that's flowing in our equivalent circuit, this current right here, is going to be the same. We're going to use the same Ohm's Law formula, but we're going to have different numbers. The source voltage of the ideal source is 12 volts. Okay, so that doesn't change. But the total resistance, when we added 40 or 400 more hair dryers, has now decreased down to 7 ohms. So what happens when we take 12 and we divide it by 7? We get 1.7. So now we have 1.7 amps. 1.7 amps flowing in our circuit. And we would need that much current flowing in our circuit if we had 40 or 400 hair dryers. Okay? Okay, so just like before, we said that if the current flowing in our equivalent circuit is 1.7 amps, then the current that's flowing in our original circuit is going to be the same, right? That's why it's called an equivalent circuit. So we're going to change this current right here to 1.7 amps. And then what we're going to do is we're going to take a look at the effect of that increased load on the voltage drop across the internal resistor that's inside the battery, okay, or inside the regulated power supply. Okay, so when we do that, what voltage do we get right here? When we take, obviously, voltage is equal to current times resistance, right? So the voltage drop across the internal resistor is going to be equal to 1.7 times 2. And what is that? 3.42. So that's 3.42 volts. Okay? So that's the voltage drop across the internal resistance. That's the current flowing through the internal resistor times the internal resistor. That's now 3.42 volts. Okay, now, when we had the first load that was 100 ohms, we found that our usable voltage at the output terminals of our actual source of power, which could be a lead-acid battery from Walmart, okay, had dropped to 11.7 volts. Okay, but now it's going to be a different value. Okay, what's it going to be now? So we'll say, what, about 8.6 volts? Okay, so now you can see that the voltage that's actually usable by these loads that are all connected up in parallel with each other has dropped from almost 12 volts, 11.7 volts, all the way down to around 8.5 volts. That's the effect of having internal resistance, which is something that occurs in all circuits. There are no circuits, aside from experimental superconductors and things like that, that have no internal resistance. All sources of power have internal resistance, and that is what limits the source's ability to supply current to an unlimited load. Okay? Because as you can see, as the current gets bigger and bigger and bigger and bigger, because our load resistance is getting smaller and smaller and smaller as we add more hair dryers or add more load, okay, then our voltage drop across our internal resistor is going to cause our usable voltage to do what? Go down. It's going to go down. And it can go down to the point that it's so low that it can't run our loads anymore. If our loads are intended to have 12 volts across them, and we started out with 11.7, that's probably not going to affect our loads very much. Okay? But when we start getting down to 8 volts, 7 volts, 6 volts, that's going to affect our loads. If we've got a motor that's inside the hairdryer, it's going to cause it to slow down. If we've got light bulbs, that's going to cause them to get dimmer. If we've got anything running, it's going to cause it to run slower and abnormally. Okay? This picture right here is really just a model, because when you go to Walmart and you buy a battery, you don't see that when you take the battery off the shelf, right, and put it in your cart, and then put it in your car and use it. But when you start hooking up more and more and more and more load to that battery, right, let's say that you're trying to drive some outrageous audio system that has huge amplifiers, right, and huge speakers, huge bass speakers. At some point in time, one battery is not going to be enough. You're going to have 2 batteries in parallel, or 3 batteries in parallel, or 4 batteries in parallel. Why is that? The reason is because your usable voltage, which is the voltage that actually appears on your amplifiers that are driving your radio system, is dropping down to a value that's lower than it can operate normally at. Okay? That's really the picture on internal resistance. It's really not any more complicated than analyzing a series circuit and then changing the value of the load to see how the value of the voltage drop across the internal resistance changes, and subsequently the usable voltage at the output terminal of the battery changes. Questions? More questions? Everybody get this? Well,
Okay.
that pretty much concludes our presentation on internal resistors. If you have anything you need to talk to me about independently, come on up and see me. Otherwise, drive safely. Have a good night.